Welcome to the Praxis Core Math, Module 2, Algebra and Functions. Functions. A function is a way of representing a mathematical relationship. A set of inputs, the domain, is set equal to a set of outputs, the range. Functions work by describing how numbers relate to each other on a number line. Function notation is the way in which these relationships are usually expressed in writing. Function notation. This is how functions are usually written. Name, in parentheses the input variable, equals the output. For example, take the function f of x equals 3x minus 5. This format shows us that this is the function f, where x is the input variable, and 3x minus 5 is the output. A specific input number can be selected by replacing the input variable with the number. This tells us to replace every instance of the input variable with the indicated number. One way to think about it is that a function is like a set of directions that can be applied in a variety of situations. The number inside the parentheses tells you what to apply to the set of directions in a given situation. Let's say that I wanted an input of 2 for the function f of x equals 3x minus 5. If I see f of 2, that tells me that I will replace every x in the function with the number 2. If I wanted to find f of 10, I would replace every x with 10. The number in parentheses will be applied to the set of directions that follow it. Function notation. When calculating the output of a function, remember to follow the order of operations, just as you would in any other equation. Some people use the phrase PEMDAS to help them remember parentheses, exponents, multiplication and division, addition and subtraction. Let's look at an example. h of t equals t squared plus 3t minus 6. What if I wanted to use 7 as the domain for this function? I would put 7 in the parentheses after h. Then I would replace each instance of the variable t with the number 7 in the output. h of 7 equals 7 squared plus 3 times 7 minus 6. Therefore, h of 7 equals 49 plus 3 times 7 minus 6. Notice the order of operations as it's being applied. h of 7 equals 49 plus 21 minus 6. Therefore, h of 7 equals 64. This shows that when 7 is used as the input for h, the output is 64. Functions in real life. One of the things that you will be expected to understand is how functions are used in real life. Consider the following situation. The height in feet of a ball dropped from 100 feet in the air is modeled by the following function. h of t equals 100 minus 16t squared. In this example, t represents the time in seconds since the ball was dropped. Now, let's use the function to determine how far above the ground the ball would be after 2 seconds. Since it has been 2 seconds since the ball was dropped, we should replace t with 2. h of t would equal 100 minus 16 times 2 squared. h of t would then equal 100 minus 16 times 4. Notice again the order of operations. h of t would equal 100 minus 64, which would finally give us h of t equals 36. Therefore, after falling for 2 seconds, the ball is 36 feet above the ground. Also notice at the end of the problem, we added our units to the final answer. Equations. Imagine the following situation. You are raising money for your school booster club. For each dollar your team raises, a group of sponsors have agreed to match your money raised with $3. How would you represent this kind of situation in a math problem if you wanted to figure out how much money you would need to raise to reach a particular goal? To do this, you would write an equation, a mathematical statement that contains an unknown. An unknown in math is represented by a letter called a variable. To vary means to change, and the variable is the unknown or changeable quantity in the problem. In the situation above, I might represent the amount of money the team raised with R for raised money, and T for the total amount earned from the fundraiser after the matching funds have been added. Therefore, R plus 3 times R equals T. With this equation, I can plug in different amounts of money raised to see what my total would be. While this example is very simple, and you could probably work this out in your head without using an equation, the process will work even when the numbers become far too complex for simple mental math. Rules for equations. One of the most important rules to remember when working with equations is that you must do the same thing to both sides of an equation for it to remain true. What if I had an equation that said 10x equals 100, but I didn't have 10 of whatever I was using? I only had 5. That's totally okay. You can reduce the equation, but you have to remember to treat both sides the same way. Whatever you do to one side, you must do to the other side. So if I wanted to reduce my 10x to 5x, I would need to divide both sides by 2. If 10x equals 100 and I divide both sides by 2, I would find that 5x equals 50. Consider the following equation. Remember that x represents a number that is unknown. 7x plus 4 equals 5x minus 2. The problem in this equation is that we have an x on both sides of the equal sign. To fix this problem and make the equation one that we can solve, we need to get all of the variables on one side of the equation. To do this, you use inverse or opposite operations to get rid of the variable on one side of the equation. Remember that whatever you do to one side of the equation must be done to the other to make sure both sides remain equal. Since I have a positive 5x, I am going to add a negative 5x to both sides. This will eliminate the positive 5x, and I will only have a variable on one side of my equation. 7x plus 4 minus 5x equals 5x minus 2 minus 5x. Notice that when I add negative 5x to both sides, the negative and positive equaled 0, causing there to be variables on only one side of the equation. Next, I combine like terms so that 7x minus 5x gives me 2x, which I still add to the 4. This is the equation with the variables isolated to one side. 2x plus 4 equals negative 2. Once the variable has been moved to one side of the equation and simplified, I am able to begin solving the equation. Now, we must undo the operations that are applied to the x to get it completely isolated. The x is being multiplied by 2 and has 4 being added to it. I must undo both of these things. First, I will undo the addition of 4 by subtracting 4 from both sides of my equation. 2x plus 4 equals negative 2 becomes 2x plus 4 minus 4 equals negative 2 minus 4. Notice that I added a negative 4 to both sides, causing the 4 to be eliminated from one side of the equation, and the other side becomes negative 6. So my equation is now 2x equals negative 6. This still leaves me with 2x, which means that x is to be multiplied by 2. The only way to get rid of the 2 that is being multiplied is to divide both sides by 2. When I do this, the 2 that is being multiplied by x is canceled out, and I am left with x alone. On the other side of the equation, I must divide negative 6 by 2, which gives me negative 3. My final answer would be written like this: x equals a negative 3. Equations in real life. Consider the following situation, where we will look at the number of points a basketball player scores in a game. The equation A plus 2B plus 3C equals P could be used to represent this. In my equation, A is the number of successful free throws, B is the number of successful two-point shots, and C is the number of three-point shots. P is the total number of points. Let's look at how we might be able to use this to determine what types of shots players made if we were missing part of the information. Let's say that a player made 3 free throws, 2 three-point shots, and scored 25 points in total, but the person keeping stats forgot to write down how many two-point shots the player made. Could we figure it out? In this situation, we have 4 variables. However, we know 3 of them. A equals 3 free throws, C equals 2 three-point shots, and P equals 25 total points scored. We can replace these variables with the number that we know, just like we did in the function example. Replacing our known variables leaves us with this equation: 3 plus 2b plus 3 times 2 equals 25. The equation will be easier to solve if we simplify before trying to solve for b. To simplify means to put things that are alike together. In this situation, the numbers are alike, so we can put them together. 3 plus 2b plus 6 equals 25. Therefore, 2b plus 9 equals 25. Now, we still need to isolate b, so we should subtract 9 from both sides of the equation. We can isolate b by subtracting 9, then dividing by 2. 2b plus 9 minus 9 equals 25 minus 9. Therefore, 2b equals 16. Next, we divide by 2 to isolate b, and remember we must divide both sides by 2. When we do, we find that b equals 8 two-point shots. Inequalities. Inequalities are similar to equations because they both show relationships between numbers. However, instead of stating that two numbers are equal, an inequality shows that something is lower or higher than another number. There are 4 symbols used to express inequalities. The less than symbol, as in 5 is less than 8. The less than or equal to symbol, as in -3 is less than or equal to 1. The greater than symbol, as in -2 is greater than 4. Or the greater than or equal to symbol, as in 5 is greater than or equal to 5. Notice that the horizontal bar underneath the arrow indicates or equal to. This means that the two numbers may be the same on both sides as in our last example. 5 is not greater than 5, but it is equal to 5, so it meets the requirements of the greater than or equal to symbol. When used in conjunction with variables, an inequality shows that the variable can have multiple correct values. For example, x is less than 3 tells us that x may be any number so long as it is a number that is less than 3. Solving inequalities. Solving inequalities is almost exactly like solving equations. Remember that solving an equation involved undoing the operations done to your variable using the inverse operation, following the order of operations in reverse. This process is also used to solve inequalities. There is one extra step to remember when solving inequalities. If you multiply or divide by a negative number, you must switch the direction of the arrow such that the greater than or less than or greater than or equal to, less than or equal to, becomes the opposite. Note that the presence or absence of the horizontal or equal to bar does not change. Only the direction of the inequality sign changes. Let's look at an example. Negative 5x plus 3 is less than or equal to negative 17. We begin by undoing the add 3 with a subtract 3, since addition comes after multiplication in the order of operations. Therefore, negative 5x plus 3 minus 3 is less than or equal to negative 17 minus 3. When the terms are combined and simplified, we find negative 5x is less than or equal to negative 20. Now we divide negative 5 to cancel out the multiply by negative 5. Since we are dividing by a negative, we must change the direction of our inequality arrow. Negative 5x divided by 5 is less than or equal to negative 20 divided by 5. Therefore, x is greater than or equal to 4. Translating words into equations. Many math problems will be presented in a verbal form instead of a numerical form. To answer these problems, we need to know how to change the problem into mathematical operations. For example, to double means to multiply by 2, or if numbers are combined, that means that they are added together. Here is a table of phrases commonly used to indicate various operations. Please note that this table does not include every word that can be used to indicate an operation, but merely offers common examples. Examples. Word problem. The sum of an unknown number and 5 is 12. This would be mathematically represented as x plus 5 equals 12. Consider the next example. Twice the value of an unknown number is 3 less than another unknown number. The mathematical representation would be 2x equals y minus 3. Notice how we used y minus 3 instead of 3 minus y, even though 3 came first in the sentence. This was on purpose. When translating less than and greater than specifically, reverse the order of the numbers being added or subtracted. Word problem. Triple the sum of a number and 5 is 12. The mathematical representation would be 3 multiplied by x plus 5 equals 12. Notice that the x plus 5 is in parentheses, and the entire parentheses is multiplied by 3. This is because the problem says triple the sum, which tells us to add x and 5 before multiplying. Linear data. linear equations express values that change at a constant rate. For example, suppose a plane is taking off and ascending at a rate of 10 meters per second. For every second after takeoff, the altitude of the plane increases by 10 meters. After 1 second, the plane is 10 meters above the ground. After 2 seconds, it is 20 meters above the ground. After 3 seconds, the plane is 30 meters above the ground, and so on. Because the rate of climb is constant, we can multiply the time spent climbing by the rate to calculate the altitude given to us in the equation. A equals 10t. In this equation, A is the altitude and t is the number of seconds after takeoff. In our previous example, the plane's initial altitude was 0 because it was on the ground. However, linear data will often start at a number other than 0 and then change by a constant rate. Suppose a different plane is 96 meters above the ground and descending at 8 meters per second. Our altitude will start at 96 and then decrease by 8 meters every second, giving us this equation. A equals 96 minus 8t. Remember, A is the altitude and t is the number of seconds after the plane was 96 meters above the ground. For this equation, if we plug 0 seconds for t, the altitude is the starting point of 96 meters. After 1 second, the altitude will be 88 meters, after 2 seconds 80 meters, and so on. Any equation or data that follows this pattern of starting with a number and then increasing or decreasing at a constant rate is linear. Dry mix. Mathematical equations can be represented by lines on a coordinate plane or a graph. On a coordinate plane, the x-axis is the horizontal axis, and the y-axis is the vertical axis. Generally, the variables that you are manipulating, the independent variable, will be represented as the value along the x-axis, and the variable that is responding will be represented on the y-axis. Some people use the phrase dry mix to help them remember this. The dependent or responding variable will be on the y-axis, thus dry. The manipulated or independent variable will be on the x-axis, thus mix. The equation of a line. A linear equation is one where the variables behave in a linear pattern, meaning that they change at a constant rate. These equations are called linear because when they are graphed, they will make a slanted line rather than a curve on the graph. Consider the equation y equals mx plus b. In this equation, x is the independent variable, the one that is manipulated. Y is the dependent variable, the one that is affected by changing x. The variable m is the slope, the degree to which the line would be slanted on a graph representing the rate of change. The variable b is the y-intercept, which indicates where the line would cross the y-axis. In the plane example, we use the amount of time that has passed to determine the altitude, so time was our x variable and altitude was our y variable. The equation of a line, slope. The slope of a line is the amount that y changes when x changes by 1. In our first example, the slope was 10 because for each second that passed our x variable, the plane's altitude, our y variable, increased by 10. In the second plane example, the slope was -8 because the altitude decreased by 8 meters for each second that passed. The y-intercept is the starting value of our y variable. The first plane started at 0 meters above the ground, so the y-intercept was 0, and therefore not written in the equation. The second plane started at 96 meters above the ground, so the y-intercept was 96. Note, our second altitude equation, a equals 96 minus 8t, doesn't look quite like our y equals mx plus b, simply because the mx and b are reversed. It could easily be written a equals negative 8t plus 96. It is simply more intuitive to take the starting number and subtract instead of starting with a negative number. If you find this confusing, look back at our lesson on order of operations and notice that addition and subtraction can be reversed without changing the result. Graphing lines. Consider the linear equation y equals 3x plus 2. In this equation, the y-intercept is 2, meaning the starting value, the y value when x is 0, is 2. The slope of the line is 3, meaning that every time x increases by 1, y increases by 3. We can express this relationship visually using a graph where the horizontal axis is x and the vertical axis is y. Graphing a line. Example. Suppose an electronics store has 40 TVs in their inventory and they sell 3 TVs every week. Let's make an equation for this data and then graph the equation. The two numbers that change in this scenario are the number of TVs the store has and the number of weeks. Since the number of weeks that pass will determine the number of TVs, our x variable will be the number of weeks and the y variable will be the number of TVs the store has in stock. For each week that passes, the number of TVs decreases by 3, so our slope, m, will be negative 3. The starting number of TVs was 40, so our y-intercept, b, will be 40. To make an equation, we will plug in our slope and y-intercept, leaving x and y since those numbers will change. This gives us the equation y equals negative 3x plus 40. When graphing this line, the starting y value, the initial number of TVs, will be 40, and whenever the x value, the number of weeks that have passed, increases by 1, the y value, the number of TVs, decreases by 3. Graphing inequalities. As mentioned previously, solving an inequality is very similar to solving an equation. The overall process is the same, but with an added step. This is also true of the relationship between graphing lines and graphing inequalities. You graph an inequality just like a line, but with an added step. To graph an inequality, start by replacing the inequality symbol with an equal sign and graphing that line as you would any other line. We will address the inequality in a moment. Y is less than or equal to 2x plus 1 becomes y is equal to 2x plus 1. As we learned earlier, this line has a starting y value or y-intercept of 1 and a slope of 2. That is, every time the x value increases by 1, the y value increased by 2. The line should look like the one on the table you see to the right. Changing our inequality to a line tells us the general shape of the graph. However, we mentioned previously that inequalities allow for a range of values instead of just one value. To show this in our graph, we shade above or below the line depending on which inequality symbol is used. If the inequality starts with y is less than or equal to, this tells you to shade below the graph to illustrate that y values are less than the line. If the inequality starts with y is greater than or equal to, this tells you to shade the area above the line to illustrate that the y values are greater than the line. We also mentioned that the horizontal equal to bar tells you whether or not to include a number in your range of values. X is greater than 4 would include all the numbers that are above 4, but not 4 itself, while x is greater than or equal to 4 would include all the numbers greater than 4 and 4 itself. When graphing an inequality, we represent the equals to bar by graphing a solid line. The graph for an inequality without an equal to bar would use a dotted line instead to show that the value does not actually include the line. The line instead serves as a boundary. Back to our example. Since our inequality was y is less than or equal to 2x plus 1, the less than arrow tells us to shade below the line, and the equal to bar tells us to use a solid line instead of a dotted one. This graph to the right illustrates how the equation would look. Thank you for joining us for the Praxis Core Math Module 2, Algebra and Functions. For additional math information to help prepare for the Praxis, please check out the other videos on our channel.